Okay, so we're going to take a look at our first lesson for the Systems of Linear Equations unit. So, in this unit, we solve problems that involve systems of linear equations in two variables. We can do this either graphically or algebraically using the substitution or elimination methods, which we're going to do in separate lessons. So first off, we're going to take a look at this exploration. The Smith family and the Harper family are going to a book fair raising money for charity. Mr. Smith pays entry fees of $11 for 3 adults and 1 child. Miss Harper pays $12 for 2 adults and 3 children. We can determine the cost of an adult ticket and the cost of a child ticket by forming two linear equations based on the information we have. So I'm going to say that X dollars is going to be the entry fee for an adult, and Y is going to be the entry fee for a child. And then I can use the two sentences I have here where it says Mr. Smith pays entry fees of $11 for 3 adults and 1 child, and I can turn that into this equation. 3x, or 3 adults, plus y, 1 child, is going to equal $11. I can use my second sentence, Miss Harper pays fees of $12 for 2 adults and 3 children, so 2x plus 3y is equal to 12 to create my second equation. Now I can solve this graphically. So what I'm going to do is I'm going to put both of these equations into slope-intercept form. So I'm going to take my first equation and say, well, if I have 3x plus y is equal to 11, then I'm going to isolate y. Y is going to equal negative 3x plus 11, which means that I have a slope of negative 3 and a y-intercept of 11. I can take my second equation and say, well, if 2x plus 3y is equal to 12, then 3y is going to equal negative 2x plus 12. Or when I divide everything by 3, y is equal to negative 2 over 3x plus 4. In this case, I have a slope of negative 2 over 3 and a y-intercept of 4. I have enough information to graph both these out. So I'm going to start by graphing the first one, where I start at a y-intercept of 11 up here. And then I have a slope of negative 3, so I'm going to go down 3, right 1, down 3, right 1, over and over again. And I'm going to connect those to say that there's my one equation. This is my 3x plus y equals 11 equation. I'm going to graph out the second one where I have a y-intercept at 4, and then I have a slope of down 2 and right 3. Down 2, right 3, down 2, right 3. And there's my 2x plus 3y is equal to 12 equation. Now, like it says, the graphs of the equations intersect at a point. State the coordinates of this point. Well, the coordinates where these two cross are at 3 and 2. What do these coordinates mean in the context of this question? Well, with these coordinates, if I take any point on my first line, like this point here, this point here, this point here, and I substitute in the values for x and y, the equation will balance out. If I take any point on the second line, then if I put those coordinates into my second equation, the equation will balance out. Where they intersect is the one case where it will prove correct for both equations, which means that this is a possible solution, the only possible solution for both equations. So if I have the point of 3 and 2, then that means that my x value is 3, my y value is 2, so the cost per adult is $3, and the cost per child is $2. So where the two equations intersect and it proves true for both x and y in both equations, that is going to be the solution. So for the system of equations, in the exploration on the previous page, we worked with the equations 3x plus y is equal to 11, and there are many different x and y values which satisfy this equation. If x was equal to 1, y would equal 8. If x was equal to 2, y would equal 5. If x was equal to 3, y would equal 2. So all those, like I was saying, would be solutions. The second equation, 2x plus 3 is equal to 3y is equal to 12. Well, if x was 0, then y would be 4. If x was 3, y would be 2. If x was 4.5, y would be 1. The only solution that works for both of them is going to be that 3 and 2. So they cross once, never cross again. The equations 3x plus y is equal to 11 and 2x plus 3y is equal to 12, considered at the same time, are called a system of equations. If you think of what a system means multiple parts working towards one goal. So when we're talking about a system of equations, we're talking about two equations or two or more equations that relate to one given problem. The solution is going to be 3 and 2 because it's the only solution that satisfies both of the equations. So let's look at a couple more examples. In this case, a system of equations has been represented on the grid. The system has an integral solution, which means that both x and y have to be integers. So if I look at this point on the grid, based on what I can see, this is going to be at the point of 2 and negative 1, which are both integers. X is equal to 2, y is equal to negative 1. The solution to this system is 2 and negative 1. And I can always write the solution as a set of coordinates. If I consider the system of equations 2x plus y is equal to 2 and x minus 3y is equal to 15, then I'm going to isolate y in both equations. 2x plus y is equal to 2, which means that y would equal negative 2x plus 2. And I'm going to graph that out. It has a y-intercept of 2, and it has a slope of negative 2, or negative 2 over 1. And I can connect the points and graph this out. I'm going to take my second equation. X minus 3y is equal to 15, which means that negative 3y is going to equal negative x plus 15, or when I divide everything by negative 3, y is equal to 1 over 3 x minus 5. Starts at negative 5, and it has a slope of 1 over 3. So up 1, right 3. Connect those points. And if I need to state the solution to the system, it's going to be the point where they both cross right here at 3 and negative 4. If I'm going to algebraically verify this, I need to prove that this solution works for both equations in their original form, because I could have made a mistake when I was isolating y in one of the equations, anything like that. So if I'm verifying I need to use the equations exactly as they originally existed and replace for x and y. So for the first equation, equation 1, I'm going to have 2 times 3 plus negative 4 is equal to 2. This is going to give me 6 minus 4 equals 2, 2 equals 2, and it works for my first equation. I also need to check it for the second equation. Just checking for one equation doesn't work because remember, you could have infinite possibilities that work for one equation, but in this case only one that is going to work for both equations. And I'm going to substitute in 3 for x again, minus 3 times negative 4 is going to be my y, is equal to 15. 3 and negative 3 times negative 4 is going to be plus 12 is equal to 15. 15 is equal to 15. And because it works for both equations, this is the correct solution.